You've seen the photos, giant stones stacked without cement, a circle on a plane that somehow tracks the sun to the minute, a pyramid so flat at its base that modern laser surveys can barely find the error, a concrete dome that has stood for almost 2,000 years while our own bridges crack after 50. Everyone calls them impressive. Almost nobody stops to ask the uncomfortable question: why does this level of engineering exist at all? Why would people without metal tools, without written equations, without cranes or computers, build things that, in some technical respects, we still cannot fully explain today? Why would they overbuild so dramatically? We are going to go through the actual evidence from laboratories, from peer-reviewed journals, from geochemical surveys and finite element modeling published in 2023, 2024, and 2025. And what that evidence shows is not mystical. It is, in some ways, stranger than mystical. It is relentlessly human. If you value rigorously sourced history that goes deeper than the textbook, subscribe right now. It is the best way to support this work. And drop a comment telling us what city you are listening from. This script is built from primary sources, including the 2023 MIT-led study published in Science Advances under the title Hot Mixing, with lead author Linda Seymour, and the 2025 Cambridge Archaeological Journal work by Gil Hackley and Avi Gopher on geometric planning at Göbekli Tepe. Deep scholarship, real numbers. Now, back to the story. Let us start 11,500 years ago on a ridge in what is now southeastern Turkey. Not a city, not a farming settlement. Hunter-gatherers, people who moved with the herds, slept in seasonal camps, had no pottery and no domesticated grain. These people quarried limestone. They cut it into columns up to 5.5 meters tall, weighing up to 50 tons each, and they stood those columns in precise circles on a hill at the northern edge of the Fertile Crescent, 6 miles from the city now called Şanlıurfa. The site is called Göbekli Tepe, which means belly hill in Turkish. German archaeologist Klaus Schmidt found it in 1994 and recognized it immediately for what it was. Not a graveyard, not a coincidence of geology, something deliberate, something massive, something planned. Excavations that began in 1995 revealed more than 20 circular stone enclosures across 22 acres, with at least 16 more rings still buried and unexcavated. The 1-acre area that has been fully dug represents less than 5% of the total site. The oldest structures date by radiocarbon to 9,600 BCE. To put that in clear terms, Göbekli Tepe predates Stonehenge by 6,000 years. It predates the Great Pyramid by 7,000 years. It is 1,000 years older than the walls of Jericho. And it was built by people who did not farm. That single fact overturns what archaeologists believed for most of the 20th century. The standard model was clean. First you settle, then you farm, then you get a food surplus, then you get religion, and only then can you build big. Göbekli Tepe burns that model down. Klaus Schmidt spent 10 years at the site and came to the conclusion that the monument itself may have been the reason people settled and farmed, not the other way around. The cathedral first, the wheat field second. Ian Hodder, one of the most cited archaeologists in the world, reviewing Göbekli Tepe's significance for the broader discipline, said in a widely circulated assessment, "Everybody used to think only complex hierarchical civilizations could build such monumental sites, and that they only came about with the invention of agriculture. Göbekli changes everything." Hodder continued, "It overturns the whole apple cart. All our theories were wrong. This is not fringe commentary." Hodder is the excavator of Çatalhöyük in central Turkey, one of the world's most studied Neolithic settlements. When the person running that dig says your entire field's assumptions were wrong, that is worth sitting with. The excavation teams have been running continuously since 1995, with the permit currently held jointly by Şanlıurfa Museum and the German Archaeological Institute. By 2025, the total area under excavation and geophysical survey covers approximately 22 acres, with ongoing magnetometry and ground-penetrating radar routinely revealing new features in the unexcavated portions. The budget for continued excavation is substantial, the interest is global, and the site gained UNESCO World Heritage status in 2018. The same year the Turkish government opened a modern visitor center, the site drew 850,000 visitors. That number sounds large until you compare it to the 14 million people who visit the Giza pyramids annually. Göbekli Tepe, which is arguably more revolutionary as a discovery, is still largely unknown outside of archaeology circles. Now to the engineering. In 2020, Gil Hackley of the Israel Antiquities Authority and Professor Avi Gopher of Tel Aviv University published in the Cambridge Archaeological Journal a computer algorithm analysis of 3 of the main enclosures at Göbekli Tepe. What they found was that these 3 structures, the largest of which measures 20 meters in diameter, were not built one at a time by trial and error. They were planned as a single project, following a coherent geometric pattern. The algorithm identified a standard deviation map showing an underlying design that regulated the entire layout. spatial hierarchies, symbolic hierarchies, organized from above, not improvised from below. Hockley's conclusion in that paper was precise. The planning methods documented at Göbekli Tepe, including the formulation of floor plans and the use of geometric relationships, were capabilities scholars previously assumed emerged only after the invention of agriculture, roughly 10,500 years ago. Göbekli Tepe pushes that cognitive line back by at least 1,000 years, possibly more. Who built it? That question is still partially open. Schmidt's team estimated, using Thor Heyerdahl's experiments with Easter Island statues of comparable mass, that moving one of the T-shaped pillars the 15 kilometers from quarry to site would have taken 50 to 75 people per week. A 1917 account from the Indonesian island of Nias of a comparable megalith construction recorded 525 people working for 3 days. Other researchers, using more optimized techniques including ropes, lubricants, and levers, have estimated that all the structures at the main excavation area could have been built by just 12 to 24 people in less than 4 months. The uncertainty range is enormous. What is not uncertain is that it happened, and that it required organizational systems no one had previously credited to pre-agricultural humanity. The pillars themselves carry intricate low-relief carvings, foxes, lions, gazelles, birds, scorpions, and in a few cases what appear to be stylized human figures with belts of fox pelt. Tool marks from flint blades and stone hammers litter the site. The raw material was quarried directly from the limestone bedrock beneath the ridge. The site also includes a rainwater harvesting system with carved channels feeding cisterns cut into the bedrock, capable of holding at least 150 cubic meters of water. This is infrastructure, not a camp, not an accident. A functioning complex built by people who, by every prior theory, should not have been capable of it. Cold, stone. 11,000 years gone. Now move forward. Move to Salisbury Plain in southern England, roughly 2,500 BCE, and you find another building problem that should not be solvable with the tools available: Stonehenge. The version most people picture, the iconic ring of massive upright stones capped with horizontal lintels, was constructed in a period archaeologists call Stonehenge III, roughly 2,600 to 2,400 BCE. The sarsen stones, which are the large ones you see in photographs, weigh up to 25 tons each. The smaller blue stones weighed between 2 and 5 tons and came from the Preseli Hills in Wales, more than 240 kilometers away. In 2020, a geochemical provenance study by David Nash and colleagues, published in Science Advances, confirmed via trace element analysis that 50 of Göbekli Tepe's 52 main sarsen megaliths match the chemical signature of Westwoods, a forested area of the Marlborough Downs approximately 25 kilometers to the north. This resolved a centuries-old debate. In 2025, Nash and his colleague T. R. Ciborowski published a follow-up in Archaeometry defending the methodology against challenges from a competing team, reaffirming Westwoods as the primary source using multi-sample statistics. The blue stones were confirmed by isotope work to have been transported by humans, not glaciers, across the entire breadth of Britain. An August 2025 paper in the Journal of Archaeological Science used strontium and lead sampling of a Neolithic cow tooth found at Stonehenge's south entrance and traced the animal's origins to Wales, dating its presence to around 2,995 to 2,900 BCE. The oxen were pulling stones from Wales. The logistics network was continent-wide. And then there is what the builders did with those stones once they arrived. The lintels, the horizontal capstones, are held in place not with mortar but with mortise and tenon joints. The top of each upright has a raised peg of stone. The bottom of the lintel has a corresponding carved socket. The lintel is lowered onto the peg and locks into place. This is carpentry, applied to 50-ton rocks on a windy plain 3,000 years before the Roman Empire. The joints are dressed to tolerance. They fit. They have been fitting for 4,500 years. The monument is also an instrument. The primary axis aligns precisely with the midsummer sunrise and the midwinter sunset. This was first formally noted by the antiquarian William Stukeley in 1720, and modern survey has confirmed it exactly. Historic England's research team, in a 2024 book published by Liverpool University Press for English Heritage and authored by Clive Ruggles and Amanda Chadburn, established that Stonehenge's architecture was designed specifically to allow views of the exact points where the solstice suns appear and disappear on the horizon, not approximately, exactly. The moon is built in too. The 4 station stones, smaller rectangular markers positioned outside the main circle, have their long sides broadly aligned with the most southerly moonrise and most northerly moonset positions, at what astronomers call the major lunar standstill, the extreme limits of the moon's rising and setting points, which repeat only every 18.6 years. Bournemouth University documented the 2024 to 2025 occurrence of this almost once-in-a-generation event, capturing moonrises relative to the station stones. The research, coordinated with the Royal Astronomical Society and universities at Oxford and Leicester, confirmed the alignment. Achieving that calibration requires decades of systematic sky observation. It means the people who laid those stones had watched the moon for at least one full 18-year cycle before they drove the first upright into the chalk. You do not build that level of precision by accident. You do not inherit it. You earn it through generations of people standing in the dark with nothing but their eyes and their memory. Let us cross an ocean. Let us go to Cusco, Peru in the 15th century CE. The Inca Empire is near its height. On the ridge north of Cusco, at an elevation of 3,700 meters above sea level, a labor force assembled under the authority of Sapa Inca Pachacuti constructs a complex now called Sacsayhuaman. The Spanish chronicler Pedro Chiesa de Leon, writing in 1553, recorded that the Inca ordered the provinces to provide 20,000 men, and that the villages would send the necessary provisions. 20,000 workers. Their task was to move blocks of limestone, some weighing up to 200 metric tons according to the highest modern estimates, and fit them together so precisely that, as every visitor to the site since the 16th century has noted, a single piece of paper will not pass between the joints. No mortar, no cement, not even sand filling the gaps. The blocks are polygonal, meaning they have irregular shapes, some with 12 or more distinct faces, and they interlock like a three-dimensional puzzle spanning hundreds of meters of zigzagging terrace wall. The longest of the three main walls runs approximately 400 meters. The average height is 6 meters. The largest stones in the lowest course reach 4 meters in height individually. How did they fit them? Jean-Pierre Protzen, an architect who published his study of Inca quarrying and stone-cutting in 1983 in a paper that remains a foundational reference, proposed that the blocks were shaped by abrasion, placing one stone against another and rubbing them together with sand and rock as an abrasive until the faces matched. Trial and error taken to an industrial scale. Weeks, sometimes months of grinding per block. The rounded corners you see on every block at Sacsayhuaman are the product of that process. They reduce stress concentration at the joints, distributing lateral loads across a broader contact area. This is not decorative. It is mechanical engineering. The walls lean inward at 3 to 5 degrees, sometimes up to 10. This pattern increases resistance to lateral shaking. Cusco sits in one of the most seismically active zones in the Western Hemisphere. In a 2024 paper published in Construction and Building Materials, a finite element modeling analysis by Lipa and colleagues, specifically of a Sacsayhuaman wall section, demonstrated that the structure could absorb earthquake ground accelerations up to 0.2 G before suffering significant damage. That matches documented major earthquakes in the region. The colonial buildings the Spanish erected in Cusco, using straight, coarse, mortared masonry, collapsed repeatedly in earthquakes in the centuries after the conquest. The Inca walls they incorporated into their foundations remained standing. The Spanish literally built on top of structures they could not replicate. What makes this over-engineering? Think about what the builders could have done instead. A simple rubble wall with mud mortar would have taken a fraction of the labor. It would have served the structural functions of enclosure and terracing. The Inca chose instead to spend years per wall section on a precision that goes far beyond what basic function requires. A precision that happens to produce walls which survive earthquakes that kill everything else around them. Whether they understood the physics in abstract terms, or whether they learned it empirically across generations of watching which buildings stood and which collapsed, the result is identical. The engineering is there. It is real. The 2024 seismic modeling paper in Construction and Building Materials provides the mathematical proof published under the agreement of Peru's Ministry of Culture and actively incorporated into the updated National Master Plan for Sacsayhuaman released in 2024, covering the site through 2030. Back to one of the oldest conversations in engineering, the Great Pyramid of Giza. Pharaoh Khufu, 4th dynasty king of Egypt, commissioned its construction around 2560 BCE. We know this from Egyptian records, from the spatial relationship of the pyramid to the rest of the Giza complex, and from a papyrus discovered in 2018 at the port of Wadi al-Jarf, which contains the journal of a logistics official named Merer, who was involved in transporting limestone from the quarries of Tura to Giza. The journal describes the supply chain in specific operational detail. It is the oldest first-person construction account yet found for the Great Pyramid. The structure contains approximately 2.3 million limestone and granite blocks. Their average weight is 2.5 tons. Some blocks in the internal chambers weigh 15 tons. The quarried granite for the king's chamber interior came from Aswan, more than 800 kilometers up the Nile. A 2025 construction management study, published in Nature Heritage Science, re-examined the logistical pace. With 2.3 million blocks placed over a construction window estimated at roughly 20 to 23 years, the average rate required was approximately 300 blocks per day, every day, for the entire construction period. Simon Andreas Schuring's 2025 paper in Nature analyzed the Grand Gallery and Ascending Passage as a potential internal counterweight ramp system. arguing that the pyramid may have been built partially from the inside out, using the geometry of internal passages to generate the mechanical advantage needed to haul stones to height. This remains a hypothesis, contested by other researchers. But it is peer-reviewed, published in Nature, and it is motivated by the same logistical pressure. The math of external ramps alone does not satisfy the pace. Now the numbers that are beyond debate. The base of the Great Pyramid is level to within 2 centimeters across its entire 13-acre footprint. 2 centimeters. That is the thickness of a finger. Across a square with sides, each measuring 230 meters. The 4 sides of the base differ in length from each other by an average error of only 58 millimeters, and the corner angles have a mean error of only 12 seconds of arc. Egyptologist Flinders Petrie made the first precise measurements of these tolerances between 1880 and 1882, publishing them in the Pyramids and Temples of Giza. His numbers have been confirmed by modern laser surveys repeatedly since. The casing stones, the polished white Tura limestone that once sheathed the exterior, were fitted with joints averaging half a millimeter wide, half a millimeter, on blocks weighing 2.5 tons each. The 14th century CE Sultan Nasir ad-Din al-Hassan stripped much of that casing in 1356 to build structures in Cairo, which is why the pyramid today shows its raw core. The orientation to true north is accurate to within 3 20-seconds of arc, an error of less than 1/20th of a degree. There was no compass in ancient Egypt. There was no fixed North Star. The sky rotated. Egyptian engineers tracked stellar transit arcs, bisected those arcs geometrically, and used the result to align a base covering 13 acres. This is not guesswork. This is documented methodology, cross-checked against the actual structure. Why? For a tomb, you need 4 walls and a roof. The engineering tolerance of the Great Pyramid is orders of magnitude beyond what the function of a tomb requires. The scholars who have studied this most closely, including Mark Lehner, who has spent decades excavating at Giza and led the 2025 construction management study, point to state power as the organizing logic. The pyramid is a statement. It is a machine for expressing and demonstrating the pharaoh's control over human labor and material at a scale that no enemy, no rival, no natural force can match. The precision is part of the statement. If you cannot hit half-millimeter tolerances on a 230-meter square, you are not in control. The overengineering is not incidental to the purpose. It is the purpose. Dead. Precise. 4,500 years still standing. Now let us go to Rome. The Pantheon. Built in the reign of Emperor Hadrian, dedicated in 128 CE, it stands today in the center of Rome as the best preserved ancient building on Earth. Its most startling feature is its roof, a concrete dome 43.3 meters in diameter, still the largest unreinforced concrete dome on the planet. No steel rebar, no post-tensioned cables. Pure concrete spanning 43 meters, 2,000 years old, not a crack in the visible surface. The dome is a marvel of graduated construction. At the base, where compressive forces are greatest, the concrete is dense and heavy, incorporating travertine and brick. As the dome rises toward the oculus, the central open eye at its crown that lets in a column of light and rain, the concrete transitions to progressively lighter aggregates, tuff, pumice, and eventually the lightest volcanic material available. The builders understood, without equations, that a dome's dead load at height is a structural liability. They reduced it systematically as they went up. Modern structural engineers studying the Pantheon consistently note that the Romans arrived at a weight distribution profile that a trained engineer in 2025 would recognize as close to optimal. But the oculus is 43.3 meters above the floor, and it is open to the sky. Rain falls straight through it onto the slightly convex floor below, which drains through concealed channels. The building was designed to accept weather as a permanent condition and handle it architecturally. It has been doing so for almost 2,000 years. Nothing about that design is primitive. Why is it still standing when modern concrete structures crack and crumble within decades? This question had no satisfying scientific answer until 2023, when a team from MIT, Harvard, and laboratories in Italy and Switzerland published a paper in Science Advances titled Hot Mixing: Mechanistic Insights into the Durability of Ancient Roman Concrete. Lead author Linda Seymour and co-senior author Admir Masic spent years analyzing concrete samples from the archaeological site of Privernum, Italy, using large area scanning electron microscopy, energy dispersive X-ray spectroscopy, powder X-ray diffraction, and confocal Raman imaging. What they found changed the standard explanation. For decades, the consensus was that Roman concrete's durability came primarily from pozzolana, volcanic ash quarried near the city of Pozzuoli on the Bay of Naples, which reacts with lime and water to form a strong hydraulic cement. That explanation was correct, but incomplete. What Seymour and Masic's team identified was that Roman concrete also contained lime clasts, small bright white mineral chunks embedded throughout the matrix. These had been noticed before but dismissed as evidence of poor mixing. They were not. They were functional. The Romans mixed their concrete using quicklime, not slaked lime. That is, they added unprocessed calcium oxide to the volcanic ash and water at high temperature rather than first neutralizing the lime in a cooling water reaction. This technique, which Massick named hot mixing, produces exactly the lime class distribution they observed. The heat allows chemical reactions that slaked lime cannot produce. It also dramatically speeds curing time and setting. But the critical feature is what happens afterward. When tiny cracks form in the concrete, as they inevitably do over decades, those cracks preferentially travel through the lime clasts, which have a brittle, high surface area nanoparticulate structure. As soon as water enters the crack, the lime clast dissolves and releases calcium. The calcium then recrystallizes as calcium carbonate, physically filling the crack from within. The concrete heals itself, automatically, without human intervention. Modern concrete does the opposite. Cracks form, water enters, the steel reinforcement begins to corrode, the corrosion expands, the crack widens, and within decades the structure requires repair or replacement. Roman concrete, absent the steel but present with lime clasts, seals its own wounds. In December 2025, a follow-up study published in Nature Communications by Seymour Massis and colleagues used newly excavated material from Pompeii's Regio 9, an intact construction site frozen by the eruption of Mount Vesuvius in 79 CE. The material was sampled between January 2024 and May 2025 under permit from the Parco Archeologico di Pompei. The analysis confirmed unequivocally that quicklime was pre-mixed dry with pozzolan before water was added, and that this sequence is what creates the lime clasts. It also documented aggregate matrix interfacial remodeling, where calcium ions from dissolving lime clasts diffuse outward and remineralize, producing calcium carbonate polymorphs that actually strengthen the bond between aggregate and binder over time. The concrete gets stronger as it ages. The Pantheon's dome is not an accident of Roman luck. It is the product of a construction chemistry that Roman engineers developed, refined, and applied with consistent intention across the empire for at least 4 centuries. But this is where the over-engineering question becomes truly sharp. The Romans had access to simpler concretes. They could have built the Pantheon with a formula that would stand for 200 years. It would have been sufficient. Instead, the dome they built has now stood for nearly 2,000 years and shows no structural sign of imminent failure. It is, in the assessment of researcher Philip Brune of Google's hardware division, who collaborated with MIT's Jackson on Roman concrete analogs, the candidate for the most durable building material in human history. Why build for 2,000 years when you only need 200? The Roman engineering answer is that you build for eternity because the emperor commands it, because the temple must outlast every rival in every empire, because the message written in concrete must still be readable when your name has become legend. The over-engineering is theological. The permanence is political. In 2017, researcher Marie Jackson led a team that published findings on Roman marine concrete, specifically the harbor structures at Caesarea Maritima in modern Israel, built between 22 and 15 BCE. Those piers contained 35,000 cubic meters of concrete poured directly into the sea, using pozzolana ash imported by grain ship from Puteoli, 800 kilometers away. As seawater percolated through the hardened structure over 2,000 years, it dissolved parts of the volcanic ash and prompted the growth of rare interlocking crystals, aluminous tobermorite and philipsite. The harbor concrete became harder as the sea worked on it, not softer. Modern harbor concrete, meanwhile, deteriorates within decades under salt exposure. Jackson's team described the Roman marine formula as a candidate for the most durable building material in human history. Piers that were poured into waves 2,000 years ago are still solid. Now look at all of this together and ask the question that makes the archaeological community genuinely uncomfortable. If this level of documented, peer-reviewed discovery is something you want more of, subscribe now and drop a comment from your city. It is the best way to keep this work going. And remember, every claim in this script traces directly to a named study or excavation report, the Hockley and Gopher 2020 Cambridge Archaeological Journal paper, the Seymour and Massick 2023 Science Advances study, the LIPA 2024 Construction and Building Materials paper, Nash and Siborowski 2025 in Archaeometry, and the MIT Pompei team's December 2025 Nature Communications publication. These are not documentaries. These are primary sources you can read yourself. Now back to the question. Göbekli Tepe was built by hunter-gatherers with flint tools using geometric planning principles that scholars previously attributed only to settled farming societies. Stonehenge was aligned to a lunar cycle that takes 18.6 years to complete, meaning the builders spent at minimum 1 full cycle observing before they drove a single upright into the chalk, and they fitted mortise and tenon joints between 50-ton stones. The Inca walls at Sacsayhuaman have outlasted Spanish colonial masonry and earthquakes by 500 years running. The Roman Pantheon dome, nearly 2,000 years old, requires no maintenance and heals its own cracks. The Great Pyramid of Giza sits on a 13-acre base level to within 2 centimeters. None of these structures is explained by the minimum requirements of its function. A tomb does not need a half-millimeter joint tolerance. A ceremonial site does not require a mortise and tenon at 30 meters elevation. A fortress wall does not need to survive a 0.2 G earthquake when the enemy is using bronze weapons. A temple does not need a dome that self-heals. The answer that emerges from the actual evidence, from Schmidt's papers at Göbekli Tepe, from Nash and Chiborowski's geochemical work on Stonehenge, from Protzen's masonry analysis at Sacsayhuaman, from the 2023 and 2025 MIT Pompeii studies, is not supernatural, and it is not the product of lost alien technology. It is the product of deep time. These cultures were building not for their generation, but for the judgment of every generation that would ever follow. The overengineering is the message. The message is, we were here, we were capable, we understood things that took effort and time to learn, and we built in a way that would prove it to anyone who came after. That is what makes the evidence so striking when you look at specific moments within these sites. In the King's Chamber of the Great Pyramid, the massive granite ceiling blocks are supported by 5 additional chambers stacked above them, a system of relieving chambers that distributes the immense weight of the pyramid's peak away from the burial space below. Engineers have confirmed this system works perfectly. The chamber is structurally intact. You could not find a less necessary design decision, given that simpler core-belled vaulting was already understood. But the Egyptians went further. They designed for forces they were measuring in experience, not in equations, and they got it right. At Stonehenge, the tongue and groove joints between adjacent lintels mean that even if one upright shifted, the connected ring of lintels would resist the movement through shared load. The structure was engineered for connectivity, not just individual stability. English Heritage's archaeoastronomy research from 2024 confirmed that the monument also tracked the 18.6-year major lunar standstill, meaning its designers lived through at least one complete lunar cycle before finalizing the layout. Decades of observation encoded in 4 arranged stones, still measurable from the correct standing point nearly 4,500 years later. At Sacsayhuaman, the blocks with the most complex polygonal shapes, some with up to 12 angles, appear consistently at points where 3 walls meet, at corners and junctions where stress under shaking is highest. The most complicated stone-fitting work is concentrated precisely where it is most needed mechanically. No written engineering manual survives from the Inca. The knowledge was transmitted through practice, through the hands of generations of stoneworkers who learned by doing what the structure required and why. The 2024 finite element paper by Lipa and colleagues, which ran Peruvian seismic records through a numerical simulation of an actual Sacsayhuaman wall section and found it stable to 0.2 G, found precisely that the interlocking polygonal geometry is the key variable in that performance. Remove the irregular faces, replace them with regular cut blocks, and the wall's seismic resistance drops. At Göbekli Tepe, the site was deliberately buried. Sometime after 8,000 BCE, the builders filled the enclosures with rubble and sealed them, preserving everything inside. That single act has given archaeologists nearly perfect context 2,025 years later. The choice to bury the site is what allowed Gil Hackley and Avi Gopher to run their algorithm in 2020 and find the underlying geometric pattern. The builders buried the evidence in a way that would protect it forever. Whether they understood this as preservation or as ritual completion, the effect is the same. You cannot separate the overengineering from the purpose. The Great Pyramid was built for eternity, and its tolerances prove that the builders meant that word literally. Stonehenge was built to track cycles that take more than a human generation to complete, which means its builders were planning for knowledge that would outlive any individual who held it. Sacsayhuaman was built to stand through earthquakes in a seismic zone with a structural method that works, without the builders ever writing down a single equation. Roman concrete was mixed hot with volcanic ash in a recipe that creates a self-healing material, and the Romans knew it worked because everything they built with it was still standing while they lived. Every one of these structures is a statement about the relationship between a people and time. Not time as a constraint, time as an audience. Consider what the workforce organization alone implies. The 2025 construction management study led by Mark Lenner, building on his decades of excavation at Giza, estimated that the peak workforce for the Great Pyramid numbered roughly 40,000 people, with an average workforce across the full construction period of about 13,200. Lenner and his colleagues have excavated a purpose-built workers' village on the plateau itself, with its own bakeries, breweries, hospitals, and administrative buildings. Analysis of human remains from the adjacent cemetery shows healed fractures and evidence of surgical intervention. These were not slaves worked to death and discarded. They were skilled laborers who received medical care, whose injuries were treated, who were organized into named crews, and who appear to have come to Giza as a matter of national participation in a project that defined the Egyptian state. Hieroglyphic graffiti left by work gangs includes team names translated as things like Friends of Khufu and Drunkards of Menkaure. These people had pride in the work. They left their signatures in the only medium available to them. The logistics of feeding 13,000 workers on a plateau in the desert required a supply chain spanning Egypt. Archaeology has found evidence of cattle delivered from farms near the Nile Delta, fish from the Mediterranean coast, timber from Lebanon for sledge runners and ramps, copper-cutting tools from the Sinai Peninsula. All of this moved on the Nile and its associated canal network. The Merir Papyrus, discovered at Wadi al-Jarf in 2018, describes in day-by-day detail a team of 200 men transporting limestone blocks by boat from the quarry at Tura to Giza. The papyrus dates to the 27th year of Khufu's reign, meaning it was written while the pyramid was under active construction. It is not mythology, it is a logistics log. There's a hillside in southeastern Turkey where, 3 meters below the grass, archaeologists have mapped with ground-penetrating radar at least 16 more megalithic ring enclosures that have never been excavated. Klaus Schmidt, who died in 2014 before half of the site had been touched, said that archaeologists could dig at Göbekli Tepe for another 50 years and barely scratch the surface. The site covers 22 acres. Less than 5% has been opened. The cisterns carved into the bedrock below the structures, capable of holding 150 cubic meters of water, suggest planning for a permanent gathering place, a place people would return to, season after season, generation after generation. Hunter-gatherers who had no permanent home built a permanent home for the thing they believed in. In 2018, Turkish archaeologists discovered at least a dozen additional hilltop sites in the rough terrain surrounding Sanliurfa, each containing comparable T-shaped pillars from the same period. Göbekli Tepe is not a lone anomaly. It is the best preserved example of a tradition. Karahan Tepe, another site in the same region, is now being actively excavated and shows architectural and iconographic similarities. The Turkish Minister of Culture called the entire zone in 2018 the pyramids of southeastern Turkey. The most recent physical confirmation of what these builders knew arrived not from a medieval chronicle or a pop science website, but from a finite element analysis paper in the peer-reviewed journal Construction and Building Materials, published in 2024, DOI registered through ResearchGate and Semantic Scholar, carrying out 3 independent Peruvian seismic simulations on a digitally modeled Sacsayhuaman wall section, finding that the structure's seismic performance derives directly from the polygonal interlocking geometry the Inca chose in the 15th century CE. No mortar, no steel, no written formula, just 500 years of watching what the mountain did to buildings and learning, in stone, how to answer it. On the plain outside Salisbury, there's a stone called the Heel Stone. It stands outside the main circle to the northeast. On the morning of the midsummer solstice, the sun rises directly above it, as seen from the center of the monument. This alignment was designed around 2500 BCE. It has worked every single summer since. It will work next summer. It worked the summer that William Stuckley first wrote it down in 1720. It worked the summer before that, and the one before that, and the one before that, going back 4,500 unbroken years. Somewhere in the organizational memory of the people who built that circle, there is an instruction that no one has found written down. This stone goes here because on the longest day of the year, the sun will rise over it. And when that happens, everyone for 1,000 years will know exactly where they are in time and space. That instruction is still working.